All right, so this slide here is very important, and which I got it from a review written by Hanahan and Weinberg in 2000 in Cell, one of the top 3 journal, called The Hallmarks of Cancer. So if you look at all the cancer, right, what do they have in common? And if you narrow it down to whether it is prostate cancer, breast cancer, lung cancer, or colorectal cancer, you will see that they most likely will have these 6 important factors, okay, that they share in common. One of the most important things that what cancer have versus normal cells, and that is typically a cell we usually do not divide, right, proliferate, and by the way, the cells divide here through the process known as mitosis, and whenever we say that, oh, this right here, if we can catch it so that it's at the metaphase, for example, we can describe them as mitotic cells. And mitotic cell is indicating that the cell is dividing. Okay, so mitotic cell. That's how you describe it. Now, they usually don't do this unless there's a growth factor. All right. That growth factor that is being produced and the cells all getting growth factor. And we can certainly take a cancer cell, you give it a growth factor, they will proliferate, they will divide. And if you don't have growth factor, then they don't need it. They don't divide out. And for breast cancer, for example, epidermal growth factor is very important. Okay, for breast cancer, epidermal growth factor is important. So epidermal growth factor, in general, I'm just going to call it EGF. Okay, so EGF, epidermal growth factor. So if you give it the growth factor, it will divide, right? And that's certainly true in an organism. Now, cancer, if you grow them in the culture, is completely a little bit different. Now, what we often see in the case of a lot of cancer cells or mitotic cells, that they are started to dividing uncontrollably. So in fact, you can say, let me write this down. Cancer cells are cells that are dividing. The key word here is uncontrollable. Uncontrollably. Okay, so you cannot control it. Remember last time we talked about cell cycle. Cell cycle has a little bit is in the mitosis, but most of the time the spin is at the G1 cycle, and then it goes into the S phase, and it goes to the G2 gap phase, and then it goes into this mitosis. But the G1S transition is very important because if you can control the G1S, you control the cell cycle. And the reason why the cell might be stopped in G1 because they lack growth factor. Okay, and now why it become cancerous then? Well, they ignore this. They go through this. Why? because it seems like the cell produced their own growth factor. Okay, so normally they don't do it, but let's say there's a mutations in the DNA, and so mutation is oftentimes, when I say mutation, uh, it could be negative or positive effect, right? Um, a mutation does not necessarily mean that you lost a gene function. You could gain a gene function through mutations. So mutations in general. So you can say, oh, there's a negative effect due to the mutation or positive effect due to mutation. So in this case, a mutation that upregulate the expressions of growth factor, right? And so now they can divide without exogenous, without the additional growth factor. So we call them, there are self-sufficient in growth signal. How are they become self-sufficient? Because they produce their own factor. All right. So that's number one, self-sufficient. All right. Let's erase all of this. Now again, we're going to look at the cell cycle. G1S, G2, and then a little bit of mitosis. Okay, this is the mitosis period. Okay. Now this is the G1S is the restriction point, if you will. Now, if the cells are if a lot of cells, it produces a lot of DNA damage, right? So they're bombarded with these chemicals, so they know that there is DNA damage. If there's a little bit of DNA damage, the cells sort of like have this mechanism to fix the DNA damage. But if it's too much, then there was like, it's not worth it. So what they're going to do is that they're going to go into this period. In fact, it's probably best for the cells to commit suicide. Okay, and so a cell that is committed to suicide will exit this, right? And we call this as apoptosis. Okay, apoptosis. and and so in a lesion, that lesion, typically what you can see is that there are uh, signal that will tell the cells to undergo apoptosis, right, to commit suicide because there's so much DNA damage. But the cells do not listen to that. Now, this is associated with a P53 I'm going to talk to you about a little bit. P53 several years ago is the one of the molecule considers molecule of the year because, in fact, many tumor, right, have a mutations in P53. And so people say, oh, maybe P53 is a marker for all cancer, if you will. Most, but not all of it. If they have a mutation in this gene, P53, then they will have cancer, if you will. It is a tumor suppressor, and a tumor suppressor meaning its normal function is to suppress it, to prevent tumor from formation. Okay, hence the name, the tumor suppressor. But if you have a mutation in P53, then you cannot have tumor suppressor happening. You cannot suppress the tumor, and so the cell will die. Okay, Now, why is P53 is part of this invading apoptosis? Is because P53 is regulating the cell cycle. It actually it detects a lot of DNA damage. It will tell the cell commit suicide, apoptosis. But if it the cells doesn't have P53, then it should go into apoptosis, but it doesn't go apoptosis, right? And so it's continue. But there, that's just one example. There are other examples that tells the cell to go into apoptosis, but it doesn't. So it's not necessary. So in this case, in this mechanism, it's not necessarily related to um, uh, more mitosis in a way. So more cellular division, right? What we do know is this: over time, you get more cells than normal, right? We call this as tumor, right? But let's say, for example, that you make two cells, right? You make two cells. So the rate of doing it is that two cells. So the point here is this: if this cell make two cells added to this pool, okay, two cells, but the out is two cells. So in other words, it's homeostasis. You produce two cells, but two cells die. You make two cells, but two cells uh, die, right? So the synthesis rate or the proliferation rate is the same as the death rate. And so the tissue become homeostasis. It's the same because you make two and two die. You make two and two die. But if you block the rate of death, and so now you make two, but there's no cell dying. You make two, but no cell dying. You make two, but no cell dying. So over time, you can see you can get proliferation. Okay. So evading apoptosis. Another important thing where cancer cell does is that it's cancer, let's say normal cell. Okay. Normal cell, what we know is exhibit, we'll call it contact inhibition. Okay. Now, this is just a phenomenon that we observe, and that if you look at the normal cell, as they're dividing, right, they will know there is a detector that somehow they're confining, that they know, okay, we have reached the limit. There's no more space to grow, right? And so if they're, here's a cell, they're dividing, right? There's space for them to divide. There's space for them to divide, but then they start touching each other. If they touch into each other, we call that contact inhibition, and they stop growing. Okay, so there are factors that it's putting out that tell it, hey, they're anti-growth signal that telling us, hey, you have reached this area. Let's do not divide anymore. But there are factors that tell them not to grow, but they're ignoring. So we call that insensitive to anti-growth factor. And so what they do, they pile up on each other. Okay. So that's why if you look at epithelial cell, right? So you can say, oh, epithelial cell, typically this is the lumen. And cells then say this is single layers of cell, simple epithelium, for example. They grow, they grow, they grow until they don't grow anymore. Because they know that this is the base and this is the apical, and they've reached their limit. But once they lose this contact inhibition, then they grow on top of each other. Okay, like that. Then it'd be carcinoma in situ, for example. So insensitive to anti-growth factor is another important. So in the future, I'm going to do is ask you what are the 6 feature that shares in a lot of tumor. You would say, oh, their cell sufficiency in growth signal, they evade apoptosis, and they're insensitive to anti-growth signaling factor. And a lot of times too, just like we talked how um, in chronic inflammation, you might have angiogenesis. Similarly, in tumorigenesis, where particularly if the tumor are getting, very big, very big, and if there's no blood supply to this tumor, then the cell, particularly in the center, would die, will become necrotic. Okay, and so what happened is that the tumor have a characteristic to develop new blood vessel within this tumor, right? And so if they want to get big, they have to sustain angiogenesis. And a lot of tumor, if they're going to start it to invade, they're going to secrete enzyme we talk about. And enzyme does is that it degrades the basement membrane. So now the tumor cell can go out. Okay? These are metastases. So they exhibit this characteristic you see here. This is 4, so this is 1, this is 2, this is 3, this is 4, this is 5. Tissue invasion and metastasis. And finally, what you see this is that 6. Okay. Okay, so let's say this is the last lesson, 6. Okay. Now, if you look at dermal cell, right? If I take out a skin and I grow it on a tissue plate, I will see that the cells started to divide. Okay, this is called 1 division. This is 2 division, right? And so forth. Usually about after 37 division, the cell will die. They all will die. Okay, and there's a guy who described this. This is known as the Hayflick limit. And what a Hayflick limit is that this it's a way of saying, oh, the cells do not have this potential to become immortalized. They can't just replicate, continue on to the end of time. There's going to be a point where they're going to die, okay? And the phenomenon for that is because if you look at the cells and the DNA in the cell, what you see is that here's the chromosome, okay? Now, typically, I don't know if you guys study DNA replication, but in the DNA replication, what it does is that in order for the DNA polymerase to make a copy of itself, it requires a primer. A primer is an RNA piece that binds to DNA, right? Then the DNA polymerase allows it to continue. We call it the primer. And then later on, it's going to remove this primer and fill it in, right? But the question is that how do you replicate at the end if you don't have any primer? Okay, so a lot of these end of the DNA is a region known as the telomere, and the telomere region is not really replicate. It can't because there isn't a primer upstream that allows it to be extended. So telomere length are usually not replicated. And one of the hypotheses would be is that this is how a cell age, it's because the telomere length will get smaller and smaller and smaller, right? Um, and there's an enzyme called telomerase. Telomerase is an enzyme. Telomerase. Telomerase is an enzyme that adds the telomere length. Okay, so what it does is that it add what is that? It add a telomere length to the end of the chromosome. Okay. So what we see is that another characteristic of the cancer cell is that they upregulated telomere activity. Okay. Telomerase activity is increased. Okay, so now they have increased. They can, if you now grow these cells, they have these inability to grow to the end of time, as you will. They become immortal, as you will. And so what happened here is that if I take some normal skin and I grow it in culture, most of the cell, boom, hit the Hayflick limit and they will die, right? 99.9% of the cell will die. There is, however, one or two cells that still survive. And in those cells, the telomerase activity will increase and then they start to repopulate. And now these cells that have increases telomerase activity, they become immortal. And immortal, in the lab, we call this as a cell line. Now you establish a cell line like the HeLa cell line, which is a cell line with this was isolated from an African American, Henrietta Lack. HeLa cell line. If you guys want to look up the HeLa cell line, it's pretty interesting too. Okay, it's a cell line. It's immortal cell line, in fact. All right, so 6 characteristics of a lot of cancers or tumor cells, and that is they produce their own growth factor, they evade apoptosis, they're not sensitive to anti-growth factor, they have ability to sustain angiogenesis, have limited replication potential because they're upregulated telomerase, and they have mechanism for invasions and metastasis. Usually, they secreting an enzyme like stromalysin, for example, that digested the basement membrane. All right, I'm going to end it here. Are there any questions